Hi, my name is JF, and I'm part of BotFactory. I do all sales and marketing, and I'm here to talk about how we used Squink to print a gas sensor, a handheld breathalyzer. We printed a rigid and flexible board and 3D printed the cases using another machine. We only used what we could find in our space to make our product. And here it is. Basic handheld device, and essentially what it does is it detects certain types of chemicals, specifically ones like ethanol, isopropyl alcohol, and so forth. And let me do a quick demonstration. So right here I have isopropyl alcohol and I have a Sharpie. Sharpie actually has a chemical called xylene. Xylene is something that the sensor cannot detect. So, typically, the volatile chemical would cause the light to turn from green to red. But if I use something like isopropyl alcohol, and I dose a little bit onto a rag, what's going to happen here is going to turn red. Very straightforward. I'm going to explain to you how it works and how I used Squink to make it, and basically what my workflow was like, how I went from A to B to C, so that you may understand how you could use Squink in your own prototyping space, college, at your office, some sort of factory space, anywhere where prototyping is done and you need to be doing it quicker. So let me just show you my presentation. So, starting from the beginning, basically we go from the product requirements. So when I started making my device, I wanted to think about a few things that I wanted to see. I wanted it to be handheld. I wanted to only use the tools that I could find in my office, no outside help. And I wanted to be able to specifically detect certain things like ethanol. The original idea was being breathalyzer, like something you would see a cop use at a sort of roadside stop, or the sort of something you could actually reasonably detect how much someone has been drinking. Because these devices aren't terribly complex. The sensors are now actually fairly common, and the math behind it is relatively well understood. So the first part is the gas sensor, and the gas sensor essentially is just a camera-resistive device. It's a semiconductor that, under the presence of certain chemicals like hydrogen or other chemicals, other elements, it will change its resistive properties, kind of like any photoresistor or something like that. The thing is that, of course, ethanol doesn't actually produce any, isn't actually hydrogen. It has hydrogen attached to it. So there's a heater that basically breaks down the molecules as it passes by. Xylene has hydrogen, but it doesn't essentially break down that easily. So that's why the sensor didn't go off in the presence of a straightforward, simple pen when it was near the sensor, but the rag covered with ethanol did, or isopropyl alcohol did. The other part that's critical was the AT-Tiny. It was simply a straightforward, simple MCU that I had. I've used on other products and I'm very familiar with. I didn't really need a whole lot of processing power, and I only needed an analog in and a digital out for sending out the signaling for the LEDs. One thing I like about it is it's very extremely low power and relatively simple to program. I used an Arduino to program it as an ISP. Squink as itself stands, its capabilities allow it to print on rigid or flexible materials like Kapton or F4. We can plate holes, which is critical because we have some through-hole components. Print 10 mil traces, and for the size limitations, these were considerations I had to keep in mind when I was designing my board. The schematic is fairly straightforward. It's basically, there's a 5-volt regulator because I'm pulling out a 9-volt battery. And there is on the right you can see a 10K ohm pot that acts as a filter, not a filter, sorry, as a sensitivity meter. Basically reduces or increases the sensitivity of the sensor by drawing some of the analog signal away towards ground. And then of course the LED. And we have one LED on the basic board, but I have another set of schematic for the 9 LEDs, which is just 8 LEDs in a ring and a resistor and a header. From the day one, basically I went from this. I went to breadboard and I programmed it. I wanted to basically see if I could prove out the concept on a most basic format to know that I was going in the right direction with the program. So I used an Arduino as a controller, pulled out libraries for NeoPixel and the gas sensor, and used the pot to determine whether or not the sensitivity could be changed, and the LED to basically see if my programming was working properly. When I went to the design step, the big question that came to my mind was, how big a trace should I make? So when you're designing a board with Squink, you have to keep that in mind. Our printed circuits are not the same connectivity as a typical copper board. So you have to do a little math to make sure that your expected power's consumption is not going to overwhelm the trace and cause a potential breakage. And so what I did is I looked at the gas sensor, and it was 900 milliwatts, which is 180 milliamp draw. I have 9 LEDs, 1 on the board and 8 on the flex circuit. That together was pulling 540 milliamps. But I wasn't actually going to be using it at 60 milliamps, probably using it half that or less. But I wanted to make sure that if I had a situation where there's too much power flowing through, I wasn't going to blow out a trace. So I went with a maximum allowed amount. AT Tiny doesn't really have any has no major current draw. So it's reasonable to assume that I had around 720 milliamp draw, 5 volts on at least one of the traces. So I went to the website, I took a look at our advanced ink listing and description, looked into the specs around what our amperage could be, and it could work. I could have printed the whole design with 15, but I went with 20 because I knew it would be bending a lot of the traces, and lower current, lower resistance means more sensitivity on the analog out. Of course, I mean, the 10K pot has a variance 10K ohm. It's quite a lot. So it's not really a big concern. I could have gone with 15 easily, but I just went with 20 anyways. So when I started making it, I went with a single layer, but it was too big, and it was just limiting me in terms of where I could place everything. And I realized halfway through that I wouldn't be able to place the flexible circuit in the way I wanted to. So, and that was difficult. So I had to change up the design, place the header in the middle, and go with a 2-layer board. Making a single layer board is like less than an hour. It's very simple. The curing process is typically what takes the longest. But when you're printing a 2-layer board, you have to do two layers of conductive ink. Conductive ink curing takes quite a long time, 20 minutes typically, for it to heat and cool. So it can be 30 minutes. So that iteration process meant that 2-layer board was about 3 hours to make. For a single layer, like an hour. But within day 2, I was able to basically get a decent working prototype that I was happy with. Day 3, I spent basically working on the flex circuit, and I exported my original sort of PCB board, my rigid board, and started doing a little bit of analysis about how my 3D printed case would look, my plastic case, and how long the flexible circuit would have to be for it to go from underneath the headers all the way up to the front of the board and then sit surrounding the sensor. Originally, my design just had one LED, and that one LED would just simply glow turn off, and I didn't really think it was very nice. So I went with a circular set of LEDs around the sensor, and that meant that I had to somehow sneak the wiring from the LEDs to the board somehow. I could have printed the whole thing with adhesive backed Kapton stuck onto the edge of the board and just, so I would have had like a Ridgeflex single design board, but that is difficult because you might screw up the design and you have to reprint the whole thing and it would take forever. So I went the modularity aspect. I had a rigid board and a flex board, and I had a header that was connected. That is the approach that I recommend other people if you want to connect rigid and flexible boards, and that's typically how most people do it nowadays. The cool thing is that I have a Squink. I could print flexible boards whenever I want. So it allowed me to sort of test and experiment and try different ideas and then print them and then go back and change anything if I wanted to. But the critical thing I needed to learn at this stage was how long to get from the header to the top of the board. And the other thing I needed to know was to orient the LEDs in such a way that it was tight enough, but the LEDs wiring for ground and power weren't going to constrain the design. They weren't going to be too wide. In the end, it worked out. As I was designing it, it seemed to kind of fit within the parameters. The full length of the machines in terms of printable area was utilized. The circuit was about 5 inches in length, so I was lucky I didn't have to change it up and see if how to getting it within 5 inches wasn't that hard, but if you have to go longer, it gets a little bit more difficult. I also needed an SMT header, and I needed to have just enough length so that the bend could be done. Now, so we typically recommend that there's a 2 millimeter radius bend. And if there's any very strong or very sharp bends, that you take some Kapton tape or some sort of stiffener, place it underneath after you've printed your board to make sure that that area is not going to bend so much that the traces break off. Luckily, I didn't have to do that, but I printed one circuit, and I discovered that at one point it would bend too much that the component would break off. Let me actually show you in a video. Okay, so when this guy is sitting on top of the sensor, it has to wrap underneath the board and then connect. And at this point, the component can pop up. See, there you go. Component pops up. That is a problem. So I had to extend the traces longer to make sure that I had better protection. And I placed some tape underneath here to make sure that it was stiff and wouldn't actually break. That is kind of one thing you might want to consider when you're doing flexible boards with Squink. Is to simply just take an extra piece of Kapton or some sort of stiffener at points at which it bends to make sure that it bends properly. But because it cost me 2 hours to make, I didn't even have to pay attention. I just printed and clicked, came back, cut it out, tried it out, didn't work, changed the design, tried again. There wasn't even very much money or time wasted, which I think is the huge value of our machine. So, moving on. By day 5, I printed the case, 3D printed the case, and assembled the whole device. And turned it on, and it worked. Worked perfectly. Worked exactly as I tried with my breadboard, my original first model, and as the sort of final prototype, this was a functional device that I could show off to someone. I took it to a party, tried it as a breathalyzer, worked great. I think that's kind of the most surprising, most amazing part about the whole thing is that I went from basic design to this within a week. I think it definitely needs improvements, and there's a lot of things that I could improve upon this. First off, I think I need some sort of IC, some sort of part that says, alcohol sensing, so and so. That's not very hard. I just need a larger processor. I need more I/O pins. I don't have enough I/O pins for an LED counter. I don't have enough for the various segments. I only have 4 pins left over. And so I would need something like some sort of AT tiny. What else? I think I could have probably redesigned the casing to be a little nicer. That is not surprising, but that's pretty easy to do. And I think that I'm comfortable enough with this design that I probably could have printed a piece of adhesive stuck to the FR4 and printed the whole thing as one piece. I've done this before. It kind of works. I would say if you're interested in doing this, we should have a conversation about this. But you need to make sure your design actually works completely well, because getting from the one circuit to the other is a bit of a boundary. You have to use very thin Kapton. The segmented approach is totally correct, but I think I could actually narrow this part by actually going with a single board. Battery might be a little too much. I think I could just get by with maybe 3 AAAs or something of that nature. It does consume a lot of power, but if you put resistors to reduce the heating, it's quite fine. I mean, I think this sensor is more than enough. Depends on how sensitive you want to have it. Really is what you're asking, what really matters. But as a basic design, I made this in a few days. If I had been working full time on this, I could have made this in 2 days. 5 days is basically the maximum because I was taking time, I was doing other stuff. I could have made this in 2 days, just the boards. And then making the case took some time, getting that right, added to it for sure. For a more experienced engineer, this was straightforward. For someone, I mean, my engineering background is on the engineering side. I was on the mechanical engineering side, so electrical is still new to me. For more complex boards, this machine still kills it. You don't have to make as many mistakes, you know what you're doing. But for someone at a student level doing a capstone project or something of that nature, having Squink is super valuable. I couldn't stress this enough. We know people that have done capstone projects and it takes them weeks because they've sent it a board, have it sent back. And I was making fairly simple mistakes that I realized in retrospect. That's kind of why Squink is valuable. We sell to a lot of schools. For a research lab or as a product development company, this is also valuable for making basic designs, for making intermediate complex designs where you would have to send something out to a board house to be made, partly because you want to show something to a client, or you want to demonstrate something to, to your own boss to see if this would be a product that you guys should be working on, or a solution to an existing problem you might have. So, with that, I have presentation material. If you want, I can send it to you. And if you're interested, I can also send you the schematics and the other material that we use to make this, like a BOM, and a bill of materials, and the actual final layout. So if you're interested in even making one of these, we'd be more than welcome to share it with you. Thank you very much. If you have any more questions, just contact me at contact@botfactory.co, and we'll take it from there. Thank you very much. Have a good day.